Hey there, awesome physics students. Let's talk about how electric motors work. Often these are called universal motors. It's just the basic idea of having a current carrying wire in a magnetic field, and if we design it right, it'll experience a force in the right places, which will give us a torque, some twisting action, which we can use to make a motor. So how does this work? Let's set it up. The way you do this is you start with some wire and you bend it into a rectangular shape or some shape similar to this. And then you pass a current through that wire that will travel around the loop of wire as shown here by the directions of my arrows. And let's say for the sake of argument this has a length on the bottom of L and a height of the other dimension as W for width. And let's also say that this wire loop is free to rotate about an axis, and the axis passes through the very center. So it can rotate like this in that direction. And to set up the forces on this, we need to put it in a magnetic field. So we're going to put it in a magnetic field that points straight down. So the B field is straight down. And then what we need to do next is think about what are the forces on the various segments of wire to understand how that produces some kind of twisting action. This first segment is not in the magnetic field. This vertical segment here, the current points up, magnetic field points down. Those are anti-parallel because we're taking the cross product there. That will produce a force of 0. So this vertical segment doesn't produce any force. This horizontal segment here, the current is to the right. So we take our right hand and point it in the direction of the current. We're crossing that with B. B points down. We push I into B, and our thumb points into the screen this way. And so the force on this top section of wire points into the screen. Again, on this vertical segment of wire here, that is parallel to the magnetic field, and so that's not going to produce any force. This segment here on the bottom is to the left. So we take our right hand, point it in the direction of the current. The magnetic field is straight down. We push the current into the magnetic field, and our thumb points in the direction of the force, which is out of the screen towards you. So the force on this bottom segment points out of the screen. And again, this last segment here is anti-parallel to the magnetic field, and so that's not going to produce any force. Okay, so you can see what's going on here. The top segment gets a force into the screen, the bottom segment gets a force out of the screen, and this is going to produce a twisting action that causes this to rotate. And we can compute the torque that this produces by just examining the forces and the distances. So the axis of rotation is through the center, that's drawn there. If we think just about the top part of the wire, the top wire, the force there, because the force we're using is IL cross B, I and B in this case are totally perpendicular to each other. So the magnitude of this is just going to be ILB. So that's ILB. And then the lever arm, or the moment arm here, is going to be the half distance here. That's half of W. So that's going to be W over 2. And that's going to cause, from my vantage point, that's going to cause rotation like that. So let's call that one positive. And then the other one is going to produce a force that is also ILB in magnitude. And again, that lever arm is W over 2. And that produces a torque in the same direction as the other one. So these two are going to add. And ultimately, our torque is going to be I times B times W times L. And this, if you'll notice, is just the area of this loop. You can write this instead, you can combine the I with the area and write it as a dipole moment. We'll avoid doing that for this simple derivation. But essentially, your current times the bigger the current, the bigger the torque. The bigger the magnetic field, the bigger the torque. And the bigger the area here, the bigger the bigger the torque. I want to say one more thing here, in that I have just represented one loop of wire. If instead of one loop of wire, if you just wrap this around many times, let's say n times, then the current will, for each of those loops, you'll get an extra current that's flowing in this direction. And so this current will be magnified by a factor of n. And so the torque will be increased by a factor of n. So if you have n loops, that will increase your torque. And you'll see all motors have multiple windings to increase the torque. Okay, so that's the basic idea of an electric motor.